Scientists need practical tools that can help them in the discovery process. But statistics is impractical, and machine learning is impractical. There's growing disillusionment within the scientific community regarding these tools. But rather than ditching statistics and machine learning altogether, what seems to be emerging is a convergence of these disciplines in a reimagined form that's better suited for the real world. My friends, let me introduce you to probabilistic programming. What's probabilistic programming, you say? Well, let's find out. Welcome to Code.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Technically, this episode is a continuation of the previous episode, but for the most part, this is a standalone presentation, so anyone can watch it. There is a section later in this video where I revisit our code using the Turing.jl package. For that section, I'm assuming that you've already watched the previous video, episode 810, which introduced the Turing.jl package. With that said, on with the show. Statistics, the way that it's taught in institutions of higher learning, is too rigid and doesn't allow for uncertainty. Machine learning, in its current form, requires too much data and often requires pristine, unbiased, and correctly labeled data. Machine learning models are often black boxes that can't be explained or audited, so no one is held accountable for mistakes made by those models. The real world is a messy place, full of uncertainty and lacking in high-quality data. In addition, society demands accountability, which will eventually lead to increased scrutiny of black box decision makers. What scientists need is a practical, transparent tool that will work with limited data and allow for decision-making in the face of uncertainty, while maintaining the core ideas behind statistics and machine learning. One potential solution is probabilistic programming. Probabilistic programming combines Bayesian statistics with advances in programming languages and computer hardware. Probabilistic programming models thrive in a world of uncertainty, doesn't require a lot of data, and are updated as new information is presented. Unlike many machine learning models, probabilistic programming models are transparent, so they're explainable and open to outside investigators. Sound too good to be true? Well, before you get too excited, let's dig a little deeper. Before we can fully answer the question, what is probabilistic programming, we need to answer the question, what is probability? According to Wikipedia, the probability of an event is a number that indicates how likely the event is to occur. It is expressed as a number in the range from 0 to 1, or using percentage notation, in the range from 0% to 100%. The more likely it is that the event will occur, the higher its probability. The probability of an impossible event is 0. That of an event that is certain to occur is 1. So that sounds reasonable and uncontroversial. But not everyone agrees how probability should be interpreted. This is where probability transcends the world of mathematics and enters the realm of philosophy. The Wikipedia article on probability interpretations asks the question, does probability measure the real physical tendency of something to occur? Or is it a measure of how strongly one believes it will occur? If you think that probability measures the real physical tendency of something to occur, then you may be accused of being a probability objectivist. In philosophy, objectivity is the concept that truth is independent of an individual's bias. If you think that probability measures how strongly one quote-unquote believes it will occur, then you may be accused of being a probability subjectivist. In philosophy, subjectivity has to do with the lack of objective reality. Partly due to this lack of objective reality, subjective probability was looked down upon for much of its early history. But with the advent of computers, subjective probability has become more widely accepted in modern times. Perhaps the best known application of subjective probability is Bayesian statistics. Despite it being named after Thomas Bayes, who is perhaps best known for Bayes' theorem, Bayesian statistics was actually developed by the famous French scholar and polymath Pierre-Simon Laplace in the late 18th and early 19th centuries. The description in the Wikipedia article on Bayesian statistics is actually pretty good, so I'm just going to quote directly from this article. I've provided all of my footnotes in the description below. So, according to this Wikipedia article, Bayesian statistics is a theory in the field of statistics based on the Bayesian interpretation of probability, where probability expresses a degree of belief in an event. The degree of belief may be based on prior knowledge about the event, such as the results of previous experiments, or on personal beliefs about the event. Bayesian statistical methods use Bayes' theorem to compute and update probabilities after obtaining new data. Bayes' theorem describes the conditional probability of an event based on data, as well as prior information of beliefs about the events or conditions related to the event. For example, in Bayesian inference, Bayes' theorem can be used to estimate the parameters of a probability distribution or statistical model. Since Bayesian statistics treats probability as a degree of belief, Bayes' theorem can directly assign a probability distribution that quantifies the belief to the parameter or set of parameters. This Wikipedia description of Bayesian statistics is essentially the description of probabilistic programming. Probabilistic programming is really just using a computer for Bayesian statistics.
Bruh.
Now, the foundation of Bayesian statistics is Bayes' theorem. So, what is Bayes' theorem? According to the Wikipedia article on the subject, Bayes' theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. Mathematically, Bayes' theorem is stated using this equation, where A and B are events, and the probability of event B occurring is not equal to 0. The vertical bar means given, which is the mathematical notation used for a conditional probability. So this equation is read: the probability of event A occurring, given that B is true, is equal to the probability of event B occurring, given that A is true, times the probability of observing event A divided by the probability of observing event B. This is a deceptively simple-looking, powerful equation that may be interpreted and applied in several different ways. The Bayesian statistics interpretation is that you can start with an initial belief about a probability distribution, and then you can update your belief based on new information. In Bayesian statistics, the probability of A is known as the prior probability distribution. This prior probability represents your initial belief about a probability distribution. The probability of B given A is known as the likelihood function. This likelihood function represents new information. The probability of A given B is known as the posterior probability. This posterior probability represents your updated belief about a probability distribution based on new information. So what about the denominator? The probability of B is known as the marginal likelihood, or as the model evidence, or simply the evidence. Calculating the marginal likelihood is a very difficult process that's been automated for you thanks to probabilistic programming. When applied to probabilistic programming, it's often helpful to look at this equation in this form that states that the posterior is equal to the prior times the likelihood. So this brings us to the actual workflow of using probabilistic programming. In this section, I will be referring back to the Pluto notebook from the last tutorial, episode 810. In the probabilistic programming workflow, there are two major parts. The first part is provided by the user, and the second part is automated using probabilistic programming. These are the pieces that the user provides. 1. Observe an event or events. 2. Build a model. And 3. Select an inference algorithm. The automated section only has one step. 1. Use the inference algorithm to build a chain or chains. And that's it. This chain or chains is the approximation of the posterior probability. So going back to our coin toss experiment, we collected our observations using a random number generator. But of course, this is the step where you would collect data for your own experiment, either in a lab or out in the field. When we created our model using the @model macro, this is the application of Bayes' theorem in the form of the posterior equals the prior times the likelihood. This line is the prior, and this line is the likelihood. So here, the parameter p is the unknown success rate for landing on heads when tossing this particular coin. This line states that we believe that the prior probability distribution for the parameter p looks like the beta distribution, with alpha and beta both equal to 1. This, of course, is naive and wrong, but this is our initial belief. And this line states that we believe that each coin toss should follow the Bernoulli distribution, with a success rate equal to this unknown parameter p. This belief seems reasonable. The variable y represents the data. But this model is a quote-unquote unconditioned model that has no idea what our data looks like. So we use the vertical bar character, which is the same character used for conditional probability, to condition our model to our observed data. Once our model is conditioned to our data, we can then use this model to update our belief about the probability distribution of the parameter p. This updated belief is the posterior probability. We cannot calculate this posterior probability directly. Instead, we need to use an inference algorithm that will attempt to, quote-unquote, infer what this posterior probability looks like based on the prior and the likelihood. In English, the word infer means to deduce or conclude something from evidence and reasoning, rather than from explicit statements. This inference algorithm is also known as a sampler. A widely used class of inference algorithms used for probabilistic programming is known as Markov chain Monte Carlo, or MCMC. So, what is MCMC? Again, I'm just going to quote directly from the Wikipedia article on Markov chain Monte Carlo. In statistics, Markov chain Monte Carlo methods comprise a class of algorithms for sampling from a probability distribution. By constructing a Markov chain that has the desired distribution as its equilibrium distribution, one can obtain a sample of the desired distribution by recording states from the chain. The more steps that are included, the more closely the distribution of the sample matches the actual desired distribution. Markov chain Monte Carlo methods create samples from a continuous random variable with probability density proportional to a known function. There are several algorithms that fall under the Markov chain Monte Carlo umbrella. The MCMC algorithms that you can use with the Turing.jl package include Gibbs, Hamiltonian Monte Carlo, Hamiltonian Monte Carlo with dual averaging, importance sampling, Metropolis Hastings, no U-turn sampler, particle Gibbs, and sequential Monte Carlo. The sampler that we used was the no U-turn sampler, but as you can see, there are several different algorithms that you can use, and Turing makes it very easy for you to try out different samplers. Please refer to the Turing.jl documentation to learn more about each sampler. So getting back to our workflow, once you select a sampler, you can then use this sampler to try to figure out the shape of the posterior probability. At this point, we don't know what that shape looks like, but we have an idea of the proportionality of that distribution based on the prior and the likelihood. So the sampler selects random values for the parameter p in the frequency of the probability distribution based on the prior and the likelihood. The sampler will examine these samples in an attempt to infer the shape of the posterior probability. The more samples it draws, the stronger the inference. The result of this inference process is called a chain. This chain is the approximation of the posterior probability. So now you may be wondering, what exactly is this posterior probability? Going back to our coin toss experiment, the posterior probability is the answer to the question, what is the value of the unknown parameter p that we should use as the success rate in the Bernoulli distribution for this coin? When using probabilistic programming, the answer is, I am uncertain, but based on the observations that I've made so far, I believe that the true value of the unknown parameter p lies somewhere within this approximation of the posterior probability distribution. Depending on your point of view, this answer may sound wishy-washy. If you're a scientist and you utter phrases like, I am uncertain, or I believe, this may trigger some toxic responses from certain individuals. Like, what do you mean you're uncertain? What am I paying you for? Or, what do you mean you believe? Don't you have a PhD or something? This goes back to the question, what does probability measure? Does probability measure something real? Or does it measure a belief? For an objectivist, there's a true value for this unknown parameter p, regardless of your belief. But let's take a look at an objectivist approach. Objectively, in order to find the true value for the parameter p, you would need to toss that coin an infinite number of times. Well, you don't have an infinite amount of time, so this approach is not practical. A more practical approach would be to start with your observations, and then back into an answer by using inference. With probabilistic programming, we were able to infer an approximation of the probability distribution around the true value of the parameter p with only 100 tosses of the coin. With this approximation, we now know where to focus our attention, so we can design new experiments based on our belief. Using probabilistic programming is a much more practical approach for the real world. So why isn't everyone using probabilistic programming? Well, let's take a look at some pros and cons. There are several reasons why you might want to consider using probabilistic programming as a scientist. 1. It doesn't require a lot of data to get started. 2. It's very comfortable with uncertainty. 3. It's transparent. And 4. It's built for the real world. There are also several reasons why you might not want to consider using probabilistic programming as a scientist. If you're looking for a number, then probabilistic programming may not be for you. If you're looking for certainty, then probabilistic programming may not be for you. Finally, speaking from my own personal experience making this video, probabilistic programming is not exactly easy to understand, nor is it easy to explain, especially if you're a beginner. So clearly, probabilistic programming has some marketing challenges ahead of it. But now that I've seen it in action, I think that probabilistic programming is pretty amazing. What about you? What do you think? Is probabilistic programming the next big thing? Or is probabilistic programming just a flash in the pan that will be replaced by the next shiny new object? Let me know in the comments below. Before I go, I need to acknowledge the Turing.jl team. Turing.jl was created by Hong Gi at the University of Cambridge. There's a video of him introducing Turing.jl at JuliaCon 2018. And here's a paper that he published on Turing.jl in 2018, along with Kai Shu and Zubin Garamani. Since 2018, Turing.jl has grown into quite a large project, so there are many contributors. Here are the team members listed on Turing's website. As far as additional resources go, there are many more tutorials included in the Turing.jl documentation. There's also a great Turing.jl resource at the personal website of Jose Eduardo Staropoli, who has generously shared his online textbook covering probabilistic programming using Turing.jl. I've provided links to all of these resources in the description below. If you enjoy using Turing.jl, then please consider going to their GitHub page, and please consider leaving them a star. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.